Hey everyone, it's Algo Penne, and I just wanted to explain the Leetcode question 450, delete node in a BST. So this is a binary search tree problem, and before we even begin reading the problem out, you want to be thinking recursion here, okay? Whenever you see BST, recursion. Let's read the problem. Given a root node reference of a BST and a key, delete the node with the given key in the BST. Return the root node reference, possibly updated, of the BST. And if you've ever done a BST problem, this structure should be very familiar. You essentially use recursion, and with that, you're always returning the root. So this will be taken care of if we remember how to iterate through a BST or traverse a BST. Basically, the deletion can be divided into two stages. Search for a node to remove, and if the node is found, delete the node. And here it gives us a very helpful example. This is actually one of the more visually helpful examples that I can show you, in which we are trying to delete the node with a key 3. Key equals 3. And it has this tree. You can see that 3 has 2 children, so we have to do something here, okay, to make sure we delete 3 and make sure that the conditions of a binary search tree are all fulfilled. But you can see here that if our code is doing what it needs to do, then 4 will actually go ahead and replace 3. You also notice here that 2 can replace 3 as well, and both are correct. And it just really depends on how we code that up. Both are correct, but it's a little bit less obvious what to do if the tree is more complicated. But before all of that, let's first consider or review, if you've done this before, how we should iterate through a binary search tree. So, let's just draw out the example here. We have 5. We want to remove 3. We have 2, 4, 6, and 7. Okay. How do we traverse a binary search tree? How do we even get to the node that we want to delete? Well, like I said, recursion is our best friend here, right? So our program is going to start at the root node of this tree, which is 5, and it's going to need to go down somehow. So how does it go down? Well, first it checks what its target value is. In this case, it's 3, and 3 is less than 5, okay? So where do we go? Well, obviously we want to go to the left, because the left node is guaranteed to be less than the root node, right? The left child will be less than the root node. So we go to the left, and here's 3. Oh, this is a very trivial example, but let's say we were looking for 4, right? Let's say the key we were looking for was instead 4. And what would we do here? Well, first we would start at 5 again. We note that 4 is less than 5, so we have to go to the left. And then we note that 4 is actually more than 3. So we would have to go to the right, and bam, we've arrived at our target, which is 4. So we know how to get to the key we want to delete. What do we do when we are there? And that's the more complicated part of this problem. Well, first of all, let's consider a more simple case, right? Let's go back to trying to delete 3 here. And let's say that there is no children. This seems extremely simple. How do we delete 3? Well, here's the previous node. We can go ahead and just set the previous left to equal to none. And that will get rid of this 3, right? This left branch will no longer exist. And we've already finished the problem for this case. If the node we want to delete has no children, then we've already finished the problem. So no children seems pretty trivial, right? Okay, what do we do instead if 3 has 1 child? For example, 2 in this case, okay? Well, the answer doesn't seem so hard there either. We have only 1 child node, so what if we just replace 3 with its child node? It seems like that fulfills all the conditions we need, right? 2 is less than 5, and obviously, as we know, since everything to the right of 5 will be greater than 5, 2 is also less than those. So it goes without saying that if there's only 1 child, then we can go ahead and just replace the node that we're deleting with its child. And how to code it up is a little more complicated, but conceptually it should be easy to understand, right? It's the same as if instead of 2, we have a 4, right? If we wanted to delete 3, we can just replace that 3 with 4, and everything is correct, right? Everything is still correct. So now that we understand what to do when the node that is deleted only has one child, we can figure out also what to do when it has multiple children. So let's go back to our example. And this example actually helps us a little bit in terms of trying to figure out what to do when there's multiple children. So there's 2 and there's 4 in this case here. And as you can see, the example replaces 3 with 4. That seems to work, right? We have 4 here instead of 3. Everything's good. All the conditions are met. Still binary search tree. But this is where it gets a little bit complicated, right? What if instead of 5, 3, 2, and 4, we had 50, 30, 20, and 40? And, just for consistency, let's make this red because we're trying to delete and get rid of this arrow. Okay, instead we had 50, 30, 20, 40, 60, and 70. And you'll see why I'm multiplying all these values by 10 in a second. So instead of 40 just being a leaf node, what if there was a node like 35, 41 here, and then maybe there's 36 here, and there's 34 here? What do we do then? We can't just use 40, all right? And well, in this case, why don't we just use 20? We could put 20 up here, and it would work. The problem is 20 can have the same problem. They can have a million things here as well. So what do we do in this circumstance? Things seem a little bit more complicated. You can't just put 40 here because what do we do with, for example, 41? Where does 41 go, right? Where does 35 go, right? It seems to run into all this conflict with the existing nodes. And this is where you realize a core concept for this problem. What would be the correct node to replace our deleted node with here? That is essentially the node we're searching for, right? And it's not extremely obvious at first, but if you think about it, there's really only one good candidate, and that is, or there are 2 good candidates, but let's just say, what are those candidates? Like, what is the concept between those candidates? Let's just consider the right side of the tree, right? Only the right side of the tree. What is the best candidate to put in place of our deleted node in this side of the tree? Because we can only choose one, right? We can only choose one node to put here. So what would be the best node in the right side of the tree to put? And there's only one in the right side, right? There can only be one. That would be 34, right? 34 would be the correct node to replace 30 with. As you can see, what is special about 34? Well, 34 is, since we know it's the leftmost node on the right side of the tree, it is the smallest node on the right side of the tree. And therefore, while it is bigger than everything on the left side of the tree by merit of being on the right side of the tree, it is also smaller than everything else on the right side of the tree. So if we just went ahead and, for example, replace 30 with 34 here, you would see that everything is correct, right? Now, just because it's the left side of the tree doesn't mean it doesn't have its own nodes. For example, 34.5. I know there aren't, it's supposed to be integers, but just bear with me, right? Let's say there's nodes that are in between 34 and 35 here, right? So it's not as simple as just setting the value of your deleted node to the value of this node, right? We have to do a little bit more after that. And that's where we really let recursion take care of it. Now, before we head on to the recursive part, though, let's also consider another node in the left side of the tree that might work. And if you follow the same logic, it's pretty clear, right? That node would be 25. And that's because of the same reasons. It's just inverted. It's smaller than everything else on the right, and it's bigger than everything else on the left. So for consistency, we will just go ahead and do it along with the example. We will use the right side of the tree to get our replacement node. Okay, there's one last thing for this problem, and that's how do we deal with this case, right? How do we deal with this little node here? Where do we put it, right? And if we just replace this value, we still have a 34 here. What are we going to do about that 34? Now, this is where the magic of recursion comes in. We're just going to let future layers of the function, so future, as the function recurses, it's going to go deeper and deeper. We're going to let the future take care of it. How? Well, instead of deleting the key, since the key has already been deleted, in this case it was 30, right? We already fulfilled that. Now, instead, we want to delete 34. And we trust that if all our cases are correct, it will be able to delete 34 in this right side of the tree, and we'll get a function that eventually it will bubble down, it'll keep going down through the layers and be able to get rid of 34 as well. Okay, so that's how we're going to take care of that. Now, I think I covered everything conceptually that you might have about this problem. Let's go ahead and start coding. Okay, so we have delete node and we have our roots. So first things first, let's think of our base case. What if the root is null? Right? Let's return none. Okay. Now we can do the basic cases when you're trying to traverse to any node on a BST. In this case, it's the node that we want to delete. We're going to compare its key to the key that we are looking for. So in this case, let's see if the value is, why am I doing left? That val is less than, I find it easier to actually have the key on the left here. So the target we're looking for, is it less than the roots value? If it is, what should we do? Well, we're going to have to modify the tree. So we're going to have to modify the left side of the tree because we know the node that is being deleted is in the left side of the tree. We're going to have to set it to whatever we do in the future to that left side of the tree. So let's see, self.delete node, root left, and we're going to set the key here. And I always do this for some reason, but this should be root.left. Self.left does not mean anything. Okay, now what about if the key is, so our target is greater than the root.value? Well, now we know that the node that we need to delete is in the right side of the tree. So here's something like 6 or 7. And we can go ahead and set our root.right to whatever the result of deleting the node in the right side of the tree is. Okay, great. So now we have the easy traversal part. So if it's not less than, if it's not greater than, then the key is equal to the node that we want to delete. The key is equal to the value of the node that we want to delete. So now we have our else case. Now remember, if there's only left and right nodes, right? If there's only one child of the node that we're trying to delete, the answer is fairly simple. Okay, we can just go ahead and, like we explained before, we can make the child be, or we can replace the node with its child. So let me just code that up real quick here. If root.left, then we're going to return root.left. And you can think of the previous layer in the recursion, stacks, right? It's going to send root.left instead of root to where it should be. Okay. Else if root.right, we're going to instead turn root.right. But what about the case in which there's 2? And you'll see how we handle that here. So let's make sure we handle that first. Both exist. This is the more complicated situation. So remember what we're looking for. We're looking for the leftmost node in the right tree. Okay, now let's set a pointer to go and find this leftmost node. So I'm going to start in the right side of the tree. All right, and remember, root is the node we're trying to delete. So cur is currently pointing to the right side of the tree. And we want to make sure that cur exists first of all, and if it does exist, it has a left node. If we've done that, then we can go ahead and just keep going left until we hit the node that we want to replace, right? So cur is equal to left. So in our example here, what we're doing is, let's say we're trying to delete 34. We're setting cur to equal to 40. Let me use red here. we're setting cur to point to 40, and then we're going down the left side of the tree. So that's what we're doing, right? Okay. Now cur is pointing at the node with the value that we need to replace the node that we want to delete value with. So how do we replace that value? Well, remember what was the node we wanted to delete? It's root, right? So root.value is now going to equal to cur val, okay? And now we should be good. Let's make sure our stuff is all good here. Okay, yeah, okay. It looks all right to me. Let's just handle the case in which neither of them exists. And then we always want to make sure we return the root once we're done. And that should make sure it bubbles all the way up to the beginning of the tree. And I'm looking at my code to see if anything seems wrong. Not immediately. All right, so we still need to make sure we delete the node, kind of like garbage collect the node that we've deleted. So let's do that here. Make sure recursively delete the node that we are looking for after we're done. Oh, and yeah, make sure our root that right to that. Yeah, because we want to make sure, for example, here, right, we got 34 into its correct place, but we still need to delete the old 34 node and make sure that's all handled. So that's essentially what we're doing with this recursive call. And if you don't trust that this recursion works, just run through an example and you'll see that these cases will be able to handle, deleting the node at the bottom of the tree or wherever it is as well. Okay, let's see, this seems kind of right. Let's go ahead and run this. And I feel like I have an error somewhere, but actually no, all the cases are accepting. So it looks good. Yeah, let's go ahead and submit this. See if everything is passing. As you can see, it's passing. So just some last notes before I end this video. I think the hardest case to understand is when there are two child nodes to the node that you want to delete. And the best way of understanding this is to convince yourself what node is the best node to put in place of the node that you want to delete. In this circumstance, in this case, what is the best node to replace the node you want to delete with? And once you've understood that, just understand the recursive step that you can use to take care of all the mess that results from trying to replace that node. Okay? Other than that, it's not that complicated. It's just using code to materialize the concepts that we can intuitively think of when we see the picture, right? Okay, that's it for this video. Thank you for watching. I'll see you in the next one.